Okay, let's get going finally. Start by going over the homework a little bit. Make this bigger. Okay, so first question is about the choice of what to condition on in this paper that came out pretty recently. Rob Trangucci, who was the first author on this paper, was in the UMSS. He graduated in 2014 or so. It was with Andrew Gelman, also Imad Ali, who was the TA for this class previous 2 years, and Doug Rivers, who runs the YouGov polling outfit. And they, in the past few years, have really used Stan for a lot of their predictions and stuff. And they were among the few, or maybe only one really, to do well predicting the last couple British elections and stuff like that. Anyway, so for this question, you know, should we be conditioning on this state presidential variable that's the average of all the polls that were conducted in that state? You want to ask yourself, like a lot of things when you're doing Bayesian, how would I draw from the prior predictive distribution for this data generating process? And you can have, you know, priors and stuff on the parameters that go into that. But when you go to draw whether person I in state J plans to vote and plans to vote for Trump or Clinton or whatever, you would first need to know the proportion of Trump supporters in that state, even though you're sort of simulating a state's worth or a sample from a state's worth of voters. And so that has more than a little bit of circularity to it. It could get around this problem if they were using past polls to predict what present survey respondents are likely to think or likely to do. So if you use, like, you know, the proportion of votes that Mitt Romney got in the previous presidential election, or maybe use some polls from the primaries to kind of gauge how strong Trump was in that state, that would be one thing. But that seems to not be what the authors did. They basically took all the polls that they had from shortly before the election and then, you know, made like a giant poll that they used to calculate the average of the vote in that state. And that's more or less equivalent to including a dummy variable for each of the 50 states as a predictor. And, you know, they did that as well, except they had a standard deviation that allowed considerable variation from one state to state in a hierarchical fashion. What putting state presidential vote as a predictor in X, so to speak, is basically like including a dummy variable for each of the 50 states and putting a very strong prior on the coefficient for that dummy variable that is centered on the proportion of Trump supporters from the polls that you're using, and has a very or zero or small variance. The nonlinear transformation to the log odds, you know, complicates things a little bit, but basically you're saying you have very strong beliefs that the coefficient on that dummy variable is equal to this, you know, average from the polls that you have. But the average of the polls that you have is the data that you're conditioning on. So it has this kind of circular nature to it. Similar thing, although they didn't condition on party ID in these polls, but it's probably been the most controversial issue in polling the past few years. Yeah, Robert.
So they say in the paper that they trained their model on polling data for immediately before the election. So, which means that their outcome, you're saying their outcome variable was polling data for immediately before the election?
Yeah.
So they had both, they had polling data from like the last poll as Y and polling data from like the two polls before that as an X?
Yeah, pretty much. That's my understanding of it. But like they're modeling at the individual level, the individual pollsters, and not totally individual because they bend it up into binomial. But yeah, that is not the most straightforward. Indeed, it's perhaps the most circular way to go about something like that. Sebastian.
There also the question I thought was just unclear is like what they were trying to answer with the paper. Like, are they just trying to describe like the demographics and like account for affecting the demographics versus like just trying to predict like right before the?
Yeah, it was certainly they were interested in making graphs and getting people to talk about these sort of things to demonstrate the idea of post-stratification, demonstrate the concept of partial pooling. But this was sort of one of these very Andrew sort of things to do with, which is kind of like explanatory data analysis, where, you know, trying to like point to interesting implications of a model that conditions on the data and then leave it up to other people to explore those things in more depth, or, you know, more trying to like make, you know, scientific conclusions about, you know, the dynamics and stuff that were going on. But yeah, it's not as if the paper had like a punchline, so to speak. So yeah, you didn't miss it.
Okay, there wasn't like.
There also weren't that many words, so I think they kind of set a new minimum for the number of words in a 50-page paper. But
there are words like graph inversion. Like I'll give 500 words.
Yeah, you tell Rob to make a bunch of graphs. That's basically how it goes. But yeah, that I think is a fair takeaway from that paper. So most controversial issue in polling, or perhaps the only controversial issue really in polling, is whether to condition on party ID. So some people say, well, this is like the best predictor we have for how people vote. Other people say, well, it's not really fixed. People can change their party identification at a whim. Mostly they don't, but they do sometimes, and they can change what party they say they're identified with, you know, to the pollster, irrespective of how they are actually classified in the voter registration thing for that state, based on, you know, the debates and the other things that happen in a presidential campaign. So it seems like this is something that you should want to be endogenous to the model. And of course, saying that, well, people who are registered to vote as a Republican are more likely to vote for the Republican candidate for president is a very thin explanation for political behavior, and pushes back the question of why, you know, some people register to vote with the Republican Party in, you know, some situations. Other people in the same situations do differently, like why it varies from state to state. Does that depend on, you know, the state laws, sort of thing? And so, you know, those are sort of maybe richer political science questions. It's certainly true that pollsters are not really interested in, you know, deep political science or political psychology questions as to why people behave. They do, but are very interested in predicting who is likely to win an election in advance. And not that there's anything wrong with that, but if your, you know, utility is entirely based on predictive performance of future data being like the actual ballots in the election, then you could use ELPD to resolve that question. You very likely find that conditioning on party identification improves ELPD relative to not. But again, that is only a predictive criterion. If your utility is based on answering some why questions, then ELPD is not necessarily the most appropriate metric for evaluating that. But you don't have to make it an either or issue, you kind of have to do so if you're doing this in, Stata or something that offers limited functionality. But if you were doing this in Stan, it'd be easy enough to write down a model. Okay, we're going to predict the vote total or the vote share for Trump, and we'll do it as, a weighted sum of conditional and marginal. So the number of Republican voters times the conditional probability that someone who's registered as a Republican votes for Trump, plus the number of Democratic registered voters times the probability of a Democrat voting for Trump, plus, other people who are not registered as Republican or Democrat, et cetera, votes for Trump. And then you can have subcomponents of your models for, each of these, including, predicting how many people that are registered as Republicans, Democrats, other, et cetera, are going to turn out to vote, or how many of them register as Republicans or Democrats in the first place. So you can certainly do this thing, estimating the conditional probability that someone who's registered as a Republican will vote for Trump, and that's obviously going to be around somewhere close to 0.9 or something like that. But you can also augment that with other parts of the model and combine them together to get their sort of prediction if you're interested in predicting an election a month in advance, something like that. Questions about that? No? Okay, rolling right along. Another one of the things that I think is relatively easy to deal with in Stan, but you're not going to see it a whole lot in the literature, is combining a model or combining what a lot of people would think is two separate models into a single model, namely the decision that people make to vote or to not vote, and combined with the decision, okay, if I'm going to vote, who am I going to vote for? And there's every reason in the world to think that those are not going to be conditionally independent, even if you're conditioning on sort of the usual suspects of your variables. If you're sort of, indifferent between whether you would prefer Trump or Clinton as president, then you're sort of pretty likely to not vote in the first place. But people have strong opinions one way or the other, are the people who are, likely to vote. And in the United States, we only get about 2/3 of registered voters voting in a presidential election. And so there's certainly a lot of, stuff going on, things like that. But, what's maybe a little bit far ahead of us in terms of actually estimating this model in Stan. But you can kind of take the words that are in the question and draw from the prior predictive distribution or something like this. So you have an integer s, the number of simulations you want to do, x, which is going to be a matrix of dummy variables indicating, what level you are on these 6 things, and then pass it to prior standard deviations. These are all going to be real arrays of size 2, one for the part, your utility for voting versus not voting, another, if you vote, utility for Trump versus Clinton, that difference. So we have scales on the intercept, what state you live in, the ethnicity, the gender, marital scale, age scale, education scale. Notice from, Nicole?
What's the function of the real bracket?
That just means this is going to be a real array, which is basically a vector, but it's size 2. But they're going to contain real numbers that are going to be my prior standard deviations and all these normal priors. Note from a frequentist perspective that the number of states and the number of genders and stuff like that are fixed from a frequentist perspective, and so it wouldn't make sense to be putting normal distributions on these. But for this, we're taking a Bayesian perspective when we draw from the prior predictive distribution. So we pull out the n, the number of rows in x, k, the number of columns in x, and we set ourselves up an s by n matrix to hold the prior predictive distribution. And then we loop over the number of simulations we want to do, allocating a vector of size k for the coefficients in the vote versus not vote model, and a vector of size k in the Trump versus Clinton part of the model. And then we're going to have 2 linear predictors on that. So this is a vector of size n called eta, and I want 2 of them in my array, 1 for each of the 2 parts of the model. Let's say I have a uniform prior on the correlation and the error terms. Between those 2, that's certainly a non-informative prior. You could go with a more informative one, and that would certainly be fine. I put the conditional standard deviation is the square root of 1 minus the square of rho there. And I allocate myself an integer called pos for position just to keep track of where I'm at. And so I loop, from 1 to 50, which is the number of states, drawing from a normal prior with mean 0 and state and scale according to the state scale thing that I pass in. This is the first one, and stick it into the pos element of beta, and then increment that so I stay in the same position as for the loop. Robert?
So are we assuming here that for our matrix X, everything's already expanded out as variables?
That's what I did here. You could certainly pass in individual like IDs for, state 43 or whatever. Anyway, so I do that for states, I increment pos, and then I do that for what's next, ethnicities, of which there's 4 of them. And now pos is going to start out at 51, draw 4 times, keep going with pos. Anyway, do that for gender, do that for marital status, do that for age, do that for education. You can always put in a check at the end to make sure that the number of things that you filled up is equal to k, or in this case, pos, because you increment it 1 more time at the end is going to be equal to k plus 1. Then you can take a draw from a normal distribution for your, on the prior for the intercept, add it to x times beta, stick it in the first element of eta. This is going to result in a vector of size n. And now we're ready to do the same thing again for the Trump versus Clinton part of the model, using the second element of all my arrays of standard deviations to fill in those priors and get the utility of voting Trump minus the utility of Clinton by multiplying x by the gamma, which I just filled up, and we have another draw for another intercept with the respective standard deviations. So after having done all that, now we're ready to loop through the observations. We draw an error term on the vote part of the model, vote versus not vote, from a standard normal distribution, and then we're saying, according to our data generating process, the person chooses to vote if they have positive utility for voting relative to not voting. So we take, the nth conditional expectation that we created above, add it to the error in utility for voting. If that's greater than 0, then the person votes. If that's less than 0, then the person stays home. But if the person votes, then we go on to the second part, where we have a draw in the error term for utility of Trump versus Clinton. This is going to be, since this is a marginal normal distribution, a conditional normal distribution using the error term from the marginal normal multiplied by the correlation between those 2, and the conditional standard deviation, which we defined above to be the square root of 1 minus rho squared. That's just the theory that we talked about before, composing a bivariate normal from a marginal normal and a conditional normal. And then, if that combination of the conditional expectation and the error in the utility for voting for Trump exceeds 0, we add that onto 1. So this is going to be 1 if the person favors Hillary Clinton, and 1 plus 1 if the person favors Trump. So we'll stick that in the S in cell of out. If the person doesn't vote, then we just put 0, indicating we don't observe whether they favor Trump or Clinton. Return the whole thing at the end. Robert.
So could this also have been done with multi-normal RNG?
Yes.
Over that? Okay.
And you pass it 2 by 2 correlation matrix. Could be done that way.
Okay.
Could be done a lot of ways.
The other question is, you mentioned in the question that it would be, you said it would be a certain belief that, certain beliefs of the parameters of the vote attention submodels be independent of the parameters of the vote choice submodel.
Yes.
But aren't they independent in this case?
Yes. And so that is a way, you could say that there's some, depending on how you set the scales of of these things. They are conditionally independent given these scales, but you certainly could do some less absurd things, although, you know, there would be people who disagree with, you know, your opinions on, you know, whether people who are, you know, more educated, okay, they're more likely to vote for Clinton, they're more likely to vote, period. So positive association between those two things. That would be, you know, something that educated people would find reasonable. Yeah, etc. Rishika?
When the second values to the out, I see the 0 and I thought we have like 1 or 2, right? So it was strong and
Yes. So I did that maybe here in a too subtle fashion. Out, if you vote, is equal to 1 plus this thing here. And that thing is either 1 or 0, depending on whether you vote for Clinton or Trump. So anyway, you get a prior predictive distribution matrix that has 0s, 1s, or 2s. And then, you know, the question didn't ask you to, but you could translate this into a stand program where you could actually condition on, you know, exit poll data or other things like that, and be, you know, estimating the row and, you know, all that other stuff along with it. Sebastian?
So could you, so like one thing we talked about the surveys is the difficulty of talking about some utility. Is there a way that you can make this as a model that you're, yeah, I guess you said that you can do data where you have, like your outcome is binary, and then you're trying to model a process that gets utilitarian.
Yeah.
Utility, and then you have, I guess what was really hard is like this idea of including logical statements.
Right. And so, yeah, a lot of the stuff in the econ literature is, you know, okay, people have these utilities that we don't directly measure. The units of them are arbitrary. So that's why we have to fix the standard deviations to be 1 here, but it doesn't matter what you fix it to. And only utility differences matter for choices. So when we see someone, you know, choose this instead of that, conditional on the observed choice we see, we know their utility was either positive or negative for these things, but we don't observe, you know, the measurement of that utility directly. And so we have to basically interpret all those things in the context of a model for what makes some people prefer what else. So it's not something that you can really get that far just by, you know, looking at the observed data. Nevertheless, like all that stuff about expected utility and whether people are actually like making these calculations or whether they're not, but they kind of behave as if they were, you know, all of that is stuff that, you know, is talked about among like, you know, grad students in all other social science programs. So anyway, it's a good thing to think about, but this is how you could do a relatively simple Heckman selection model with binary outcomes. At least this is the prior predictive distribution for such a model, and then it's a, you know, another step to get the posterior and then the posterior predictive distribution for a model like that. Okay, need to roll along here. Part B, how would you do post-stratification? It's really not hard at all. If you have a vector of population shares, that is the proportion of people who are this or that type, according to the intersection of the variables that you're conditioning on, then you can create a data set with like the expand grid function that will make 1 row for every possible combination of these 6 variables that you give it. Apparently that comes to 33,561. And then you have a vector of population shares of the same size, non-negative, adds up to 1. So simplex vector. You get like the posterior probabilities with posterior limpred, transform equal true. That's going to give you a S by 33,561 matrix. Multiply that on the right with matrix multiplication by your vector of population shares. And now for the population as a whole, you have this sort of, basically the population shares gives you the marginal probability that you're this or that type of person in the population, and you have these conditional probabilities that come from your model in posterior limpred. Take conditional probability multiplied by marginal probability, sum it up over all the possibilities, and you get a marginal prediction for whatever you're talking about in the population. Rashika.
So when you do the in this case for the PT, like you get the matrix with like zeros, ones, and twos, right? Or
So in this case, it would be zeros and ones, or the outcome is zeros and ones. Posterior limp-red with transform equal true is going to give you probability of 1, so that is a continuous number. If you've done posterior predict, then you would get zeros and ones. You could do the same sort of thing, but it's going to be less efficient. You're going to need more draws from the posterior distribution to get the same precision in the inference about the population because of the discreteness of the zeros and ones.
I mean, it's not related, but that was the prior prediction, just like the separate model.
Yeah, this is sort of like how would the paper do what the paper did. It doesn't really correspond to the Hegman thing, so maybe I should have put the questions in a different order.
It seemed to me that doing element-wise multiplication would give you the percent of population times like a weighted, basically like a weighted version of the prediction. Can you explain why you do matrix multiplication?
Yeah, so if you took each element of pop shares, multiplied it by the corresponding column, added it all up, that would also be.
Oh, there's like column sums of.
Yeah,
Oh,
and so that's really just what matrix multiplication is.
I get it. Yeah.
But yeah, you could loop and all that, but yeah, so post stratification, one, is a controversial thing, like frequentists don't like it. And it sounds like it's really complicated, but it's actually like 3 lines of code. So it shouldn't stop you from doing. Next question, using the GSS data, try to come up with a model for predicting support for same-sex marriage. And so using BRM and using these group-specific terms. So here I'm allowing the intercept in ordinal model to vary according to what religion the person was raised in or at age 16, as opposed to what religion they are currently. Also, the year is a factor, whether the person is a man or a woman, and I'm putting a non-linear smooth, or saying that, utility for this issue is related in a smooth but possibly non-linear way to the year in which the person was born. Certainly, older people have spent a greater proportion of their life, in a situation in which marriage is only between men and women, etc. So if we look at the default priors for those, you can see they're not filled in for the B's, and so this is a choice that is made in BRMS that, if you don't specify priors on those, then they're just going to use improper priors on the coefficients. Not the best of ideas, and the homework said not to do that. And so you can do a bunch of calls to set prior, class equal B, which is the coefficient, even though we've referred to coefficients as betas, and the intercept and the standard deviation as to how much it varies from one religion to the next, and how wiggly your nonlinear term on age is, then sort of concatenate all those together, call BRM for real, family equal cumulative, and it'll estimate this model. I think it took me like 20, 30 minutes, something like that, for it to run, but it was not outrageous amount of time. Then there's a variety of ways that you could go about demonstrating how the effect varies by age. Paul has a pretty nice one that you can just do a plot of the marginal effects thing. And so you can see the way I coded it. One was strongly disagree, I think. Yeah, so 1 was strongly disagree, 2 was disagree, etc. Up to 5, which was strongly agree. So people who were born like before World War II have a like very high probability, all other things being equal, of strongly disagreeing with same-sex marriage. But as you get into millennials and stuff, having a very low probability of strongly disagreeing with same-sex marriage. Got to keep all the negations and whatever the opposite of negation is straight. And then up to the other categories and so forth. So among people who were born in like World War I, very low probability of strongly agreeing, but higher as you get into people who were born more recently. You could do this yourself with posterior lead pred or a bunch of other stuff. Could estimate a linear model on year born, centering it in 1960, scaling it by 10, just because like a 1 year difference probably not likely to make too much of a difference, and then print out the LU to do your model comparison. I think I accidentally put like show equal false or whatever. So, but you can do stuff like that. Questions about the GSS? Question? No? Okay. Okay. Yes.
That output of LU, I know it's not shown there, but
Yeah. So.
ELPD diff, ELPD.
Right. So that should be like the difference in ELPD between the models that you give it and the standard error of the difference. And so, you may find that you're basically indifferent or, depending on what model you did. Nathan, I'm
Does it mean when it says like error data points, there's not the same amount of data points in both these models?
Oh yeah, that's a problem. You can only compare models on the same data. So you probably included or excluded a variable that had missingness on it, and so it changed. Right. So if you want to do that, you should estimate on the least common denominator sample. So if you're thinking about, okay, I could include this variable or not, but if I do, my n is going to be reduced, then you need to use that reduced n and data points even for the model that omits that variable. And so then you can do LU and you can use the observations you excluded as like a testing set that you can predict it to. Robert.
So I did take a question about this and you answered, but I did use the all caps LU from VRMS and still got the, like, it tried to round a matrix and got non-invariant values error.
Okay. You should make sure that you have the latest value or latest BRMS.
I might not have the newest RStan. Or RStan.
Well, RStan arm shouldn't have had any effect on BRMS. Anyway, the TAs or whatever can look at it, but yeah, it ran for me.
And is there any reason to believe that having issues like divergent transitions in the model would make LU great?
Well, it can undermine the assumptions of the calculations. Like basically, when you have divergent transitions, you're saying, I did not draw from the whole posterior distribution. I missed part of it. And so like then kind of all the calculations are suspect. But
they should still run.
It runs, yes. It invalidates the assumptions. Yes. No, not that they should be ignored. You should fix it before then doing this. So I had to bump up my adapt delta from 0.8 to 0.85 to fix a few divergent transitions the first time I did the nonlinear model. With the linear model or just centering and scaling, I could use the default value and it didn't get any warnings.
Okay.
But yeah, depending on what predictors you included, yours could have been better. But anyway, fix the divergent transitions, the max tree depth stuff before you like do anything like prediction or LU or any of that.
And if bumping up that delta way up doesn't fix anything, the answer is just to like try different predictors or try different priors or something like that.
Yeah, I mean, your syntax defines a valid posterior distribution, but Stan is basically saying like, this one is so complicated and it's changing so quickly across the parameter space, like the kernel is changing so quickly across the parameter space, that I can't draw from it the whole thing. And so oftentimes you're better off with maybe like a simpler model that yields a posterior distribution that can at least be sampled from reliably. And then, maybe try to tweak some stuff to do, a model that's more interesting. Yeah, like the Stan language will allow you to write down almost any model that's differentiable with respect to the parameters, but that doesn't mean the Stan algorithm can, sample from it effectively. All right, third question was an article about the National Children's Study, how we should think about doing hierarchical models for a situation like this, which is described on that article. So as it was originally designed and explained in the article, they were going to do a fairly conventional cluster sampling thing, albeit it was, not conventional in the United States to do a study that big. Other European countries have done so-called birth cohort studies on like a large segment of births, but in the United States, that is not something that we typically do. But the design of the sampling was fairly conventional cluster sampling, where you had counties or groups of counties that were adjacent, selected at random or selected at random in proportion to the size of the population that they constituted. And then within those selected counties, women who were eligible were invited to participate in the National Children's Study if they were or planned on becoming pregnant. Somehow, for some reason, basically like a single-digit number of women accepted the invitation to be in this study, which was disappointing for people who wanted there to be a sample of like 100,000 collected over 4 years. Anyway, but the sampling design was pretty conventional. Of course, accepting the invitation and, even after you accept it, do you drop out over the 20 years that they were proposing to monitor your kid? Those would obviously be not random, but you could do reweighting schemes after the fact, because the demographics of the counties are pretty well known from the census. Not like survey weights are perfect and they're extraordinarily complicated. But you could at least do something like that. However, due to their astonishing lack of success in the pilot program, someone at the NIH, a light bulb went off over their head, and they came up with a revised design where, rather than like wandering all over the country looking for women who would agree to be in the study, they would just hang out at hospitals and wait for the women to roll up in an Uber or whatever. So they would select hospitals at random in proportion to the number of babies delivered at that hospitals, and then within hospitals randomly select which women to invite to participate in CS. But in that situation, you can't really rely on reweighting to bail yourself out because we don't know what the demographics of babies are at the hospital level. We know it by like zip code, but we don't really know it by hospital, at least not as well as we know the census data. And so basically you had to get a sample that was representative the first time, because you're not going to be able to say, well, we'll salvage this by reweighting. So either way you do it, whether by counties or by hospitals, from a frequentist perspective, it does make sense to acknowledge that the babies are not independent with each other within primary sampling unit being county in the first scenario, hospital in the second is that you could have correlation in the error terms for your ultimate outcomes that you're measuring as the kids grow up. And so from a frequentist perspective, it would make sense to include random effects. So hospital level intercepts maybe allow some of the parameters to vary by hospital, things like that. But variation in the outcomes from primary sampling unit to primary sampling unit is not that interesting from a substantive medical or social science perspective. And that's really why frequentists refer to these sorts of things as nuisances that need to be integrated out. And so you can make inferences about the population as a whole. But there is variation in the outcomes, presumably by primary sampling unit, but that's because babies are not randomly allocated to primary sampling units, whether those are counties or whether those are hospitals, because where you're born has a lot to do with like what hospital you live closest to, and residential demographics where people live and stuff is highly concentrated by race, by income, by education, by basically, you know, all the usual social scientific things that at least the social scientists would be interested in. And even if they're not, the law that authorized this study said you have to, you know, investigate disparate impacts of all sorts of stuff by race. So the NIH had to be interested, even though medical researchers might not, you know, be as interested in those social science things. So what applied researchers would want to do is to introduce random effects but do it by categories of things that are not randomly sampled by level, such as race, income, education, etc. You have, you know, all of those if you do a 100,000 person study. And so what the, you know, people who are doing applied research want to put, you know, random effects on are not the things that are actually being randomized in one of these two-stage designs. And so that yields, you know, inconsistency, although it's not really an inconsistency from a Bayesian perspective. We're not interested in the behavior of an estimator conditional on the thing that it's trying to estimate across data sets that could have been drawn to constitute the national children's study. Rather, we're interested in how our beliefs about the data generating process changes conditional on the 1 or 0, in this case, data sets that we have that are going to be made available. And so it makes sense to say that the outcomes of interest may have quite a bit of heterogeneity, depending on race, income, those sorts of things. And then we put priors on the degree of heterogeneity, the standard deviations and stuff like that, and update our beliefs about those along with everything else in a joint posterior distribution. Questions about that? So this study, I think, highlights a lot of issues. One is, well, the frequentist idea of what if we were to do this over and over and over is sort of, well, there's a variety of reasons why that's not that interesting a question, but it's also a ridiculous question in this context where the people, you know, doing this spent 12 years and blew through $2 billion and didn't do the data collection once. Like, what do you mean what would happen if we were to do this over and over and over again? You demonstrated that you're completely incapable of administering something like this even once. But moreover, you know, okay, so people don't really care the behavior of the estimator across samples. But moreover, a lot of people in the medical community didn't even care if the data were representative of the population in the first place. Now, it's hard to get away with saying something like that if you're a social scientist, but if you're sort of, you know, staking your career on curing a rare disease in babies, you don't really, you know, care that much about estimating the prevalence of this, okay, it's 1%, 2%, you know, whatever it is, I'm going to develop like a cure for that. But that puts you at odds with the way these maximum likelihood and, you know, frequentist sampling things were originally conceived of back in Fisher's day, where sort of the end goal of analysis, I'm going to estimate the frequency of sudden where babies die because of cribs. Like, I'm going to estimate the prevalence of that in the population, get my estimate, and then like call it a day. Whereas the things that we're doing with social science and medical research and things like that are much more, you know, ambitious. Can we develop cures? Can we develop alternative treatments? You know, things like that. And so, you know, if you're trying to develop one of these, you know, cures, presumably your drug or whatever will, it may not, but at least going into it, you should presume that it kind of works the same way biologically, whether this is a rich baby or a poor baby or a black or a white, you know, whatever. And so those sorts of things that we know from social science yielding a lot of variation in the observed outcomes, not a super high priority for them. What they were really interested in was having, you know, a sample that was so big that there would be, you know, a few people with each kind of rare disease that they could go and, you know, do studies with. And so there's enormous pressure to just be like, get whatever data you can. And, you know, not that they were saying this because they are not Bayesian for the most part, but, you know, okay, if it's not representative, then post-stratify it after the fact, you know, to make it representative of the population, if that's the sort of inference that you were interested in making. So this was, yeah, a disaster. Not a stretch to say that. And a failing on all kinds of people's part over like 3 different presidential administrations over, you know, more than 10 years or whatever. But the last person to fail with this was me because I was a consultant on one of these things trying to evaluate the research design. And the thing that we gave to the people at the NIH basically said, if you do this by hospital, you're going to need like 500 hospitals. And that was way too expensive for the dwindling budget that they had left. So they wrote it up in like a report for the outside review people that Congress mandated to do, and they actually lied about it. They said we said could get away with 200, which is not true. They threatened to fire us if we told anybody, but they already got fired, so I can tell you. But, you know, I had alternative design where we sort of stratified it by income and stratified it by hospitals. You kind of had to like cut up your hospital by whether the people were coming from zip codes that they were rich or poor, but actually could do that and get it, you know, pretty good effective sample size and stuff like that with 150, 200 hospitals, that sort of thing. But I wasn't able to convince the other people that were hired to consult on that thing to forward that recommendation to the NIH. They were not yet convinced that something like that would work. It certainly hadn't ever been tried before. So I couldn't convince enough of the people to go that way, even though that was the only thing that we had that we thought wouldn't fail. So that never got there. And eventually Collins decided to, you know, basically abandon the project. And he may have been out to sort of sabotage it from the beginning. I don't know. But it's, you know, it's sort of a way in which science or social science and quantitative estimation, you know, meets a lot of the real world stuff that has to go into studies like this, particularly the way a lot of studies are done now where, you know, it's the government or maybe some big corporation that's making the data available, and, you know, all kinds of people use it. And so if things are sort of breaking down at that choke point of like someone, big corporation, big, you know, government agency, something like that, has to get their part of it done before all the other people who want to do research on these sorts of things can proceed, then, you know, you have to be taking all that stuff into consideration. Questions? All right. So we've got a little bit of time left to do some more stuff with Stan. All right. Always have time to disclose the fact that you're at Columbia, I'm at Columbia, Stan's at Columbia. Don't do everything related to Stan through Columbia. Columbia requires you to earn or disclose the fact that you earn. But and by the way, when the NIH paid me to like do this consulting thing, Columbia was just like, yeah, we don't want to be associated with this at all. Just take their money. We don't even want indirect costs. Just keep us out of it. So. So bowling, more fun. What if you observe J bowlers who maybe are entering some kind of tournament to see who can get the highest bowling score? How might you do a hierarchical data generating process for something like that? So here we're conceiving of pi as being sort of the overall probability of knocking down this or that number of pins in the whole across all the bowlers in the tournament, and we have shape parameters alpha for that. We have rho, which goes into the prior on the probability that the jth bowler knocks down 0, 1, 2, 3, 4, etc. pins, and so this is scaling up or down the overall thing, and so rho basically captures how much concentration there is around the average bowler from, you know, one individual bowler to the next. And then we're using the group specific, or group specific in this case is really individual bowler specific vector of probabilities, simulating the first roll of a frame of bowling from a categorical distribution like we did last time. Second roll conditional on the first roll, renormalizing the probabilities, but again, using the J-specific probability vector. And so we've taken a model we did last time, which was relatively simple, and now we've made it into a hierarchical model where we have bowler-specific parameters, indeed 11 of them. Questions about what we've done here? Hierarchical model. So this is, you know, why I say that for Bayesians, just doing hierarchical model is the most like natural thing, and doing a model where you're saying, okay, everyone has the same probability of getting a strike is like not realistic, but moreover, it's not interesting given that you find modeling bowling to be potentially interesting in the first place. Like if everybody has the same probability of getting a strike, then, you know, why have a tournament? Slave.
So yeah, in this case, like pi is also the same as like in the case we had last time. It's just like we for one bowler, like how the intellectual is that they get a specific number of things done.
Yeah. Right. But you have, you know, your specific vector on the simplex, but you presumably don't deviate that much from bowlers as a whole, or bowlers in this tournament as a whole. And, you know, how much one bowler differs from the norm is captured by rho, which we're also estimating, but we can put a prior that says like not that much. Update our beliefs about all these things. All right, so data block looks more or less the same. I've just had to add an additional index on the front of my data table saying that I have J bowlers. And so I have an 11 by 11 thing for each bowler saying the number of times this or that happened on the first and second roll. some corresponding adjustments in the transform data block. Now in my parameters block, I have pi, overall pi, which we had last time, but overall pi was the only thing that we had last time. Now I've added a simplex of 11, which I'll call pi underscore j, and an array of those. So I have one for each of the capital J bowlers. And this non-negative parameter rho capturing the concentration in these simplexes around the sort of average probabilities captured by pi. So I want to put priors on all this stuff, but actually use the jth bowler specific one in my model block, which is here. So I have my prior on pi and I have my prior on rho. Now I want to loop over bowlers. So I'm going to just extract out the jth one so I don't have to do so much indexing. Call that pi underscore. Now I basically have my prior on the ability of the jth bowler, just given by this, is a function of overall characteristics of bowlers as a whole. Okay, so we got our prior. Then we're basically doing what we did before, just using pi underscore or pi j rather than the overall pi. So we have a multinomial for what happens on the first roll. We have a multinomial for the second roll if you get a gutter ball on the first roll, so all 10 pins are left standing. And then looping from 1 to n, or 1 to 9, if you don't get a strike, don't get a gutter ball, how many pins you have remaining, renormalizing the probabilities, and you have a multinomial for the remaining pins, giving your renormalized probabilities, and that's it. So basically all we had to do was introduce some more parameters, specify our prior on the bowling specific simplex, and then rather than just doing it once, do it in a loop over all the bowlers. Okay, so what we didn't get to talk about last time was the generated quantities block. So this comes last in the STAN program. It's executed not every leapfrog step, but it's executed every iteration. You can declare more endogenous unknowns, so that should be unknowns there, assign to them, use them, etc. The samples are going to be stored. It doesn't do constraints. You can reference everything or anything in the previous blocks except for stuff in the model block. So things in the model block are off limits. Sometimes that means you have to repeat some of your calculations. So you can do all this stuff in R afterwards. Sometimes it's easier to do it just in the STAN program. It's certainly more explicit. But use it for things that are interesting functions, like we'll do below, but don't go into the likelihood. The posterior predictive distribution, functions thereof, like utility or whatever. If you need to come up with a matrix that's S by N of log likelihoods in order to pass to Lou when you get back to R, you can construct that in the generated quantities block. But what I do here, in just this short one, I create an integer vector of size j to record the score of a person according to the model over 10 frames of bowling, and I construct an integer that it corresponds to who has the highest score. And so I loop through the number of bowlers, call a function, which I'll explain in a bit. I put in the functions block called bowl game, giving the jth person's probability vector. And then it's going to do basically a random game of bowling. Conditional on that probability, you get a score. Do that for all j bowlers. And then I can sort the scores from biggest to smallest with sort indices, pull out the first one and say, okay, bowler number 26 had the highest score for this. And so if your utility is based on like plastic bowling trophies, you can use this to compute the probability that someone will win the tournament conditional on your model. And so this is an example of calling a user-defined function that is defined in the functions block, but I'm calling it in the generated quantities block to do something that is of interest, but doesn't go into the likelihood. So your overall score is not really being modeled here. It's just how you do on each roll of each frame. But what is ultimately of interest is probably your like total score. So what does this function do? This is basically just drawing from the predictive distribution of a game of bowling, takes in a vector of probabilities, a simplex vector, that can be, in this case, is specific to the jth person, initialize the score to 0, roll 10 frames where you're drawing x1 from a categorical distribution. Categorical distribution in Stan starts with 1, so you need to subtract 1 from it to introduce a small probability of rolling a gutter ball. If you get less than 10, then you need to do a second roll, given how many pins were left remaining. So that loops through the 10 frames, but the 10th frame is actually special. So if you got a strike on the 10th frame, then x1 is going to be 10. You pick it up for here. You get to do your second roll on frame 10, even though you got a strike on the first roll. And so if that is also a strike, then you get a third roll. All of these get added onto the score. But if that's not a strike, then you have a possibility of getting a spare on the 10th frame. And if you do get a spare, then you get a third roll with all 10 pins left. You have opportunity to knock down more pins, etc. So anyway, you go through all of that. You've accumulated up your score from a game of bowling, given the probabilities that were passed to that. And so we get 4,000 draws of how each person in the tournament, a distribution for how the model predicts they would score, and posterior distribution of this integer variable here. What's the ID number of the person who wins? And so like the probability that person number 26 is the proportion of times that win is equal to 26 in the posterior predictive distribution. And so really all this stuff relating to like utility or the ultimate scientific interest of the things that you're doing is often going to be computations in the generated quantities block, or just do it in R afterward. You could do the same thing writing yourself a R function, but oftentimes it's more convenient to just sort of keep as much as you can in the same language. So a few more things to talk about when we pick it up next week, but overall next week we're going to be continuing to see applications of how Stan is being used in situations where people are writing their own Stan models rather than relying on RStanArm or BRMS to do the code for them. So look forward to that.